Here's an example of something that's called a JK flip-flop. The J and K inputs of the JK flip-flop are named in the honors of someone who has invented the integrated circuit. His name was Jack Kilby. Okay, and he was a um, employee of Texas Instruments in 60s. I forgot what year it was. I'm pretty sure a lot of you are going to comment on that now. That person has done something remarkable. He has invented a integrated circuit, and you can see all the history. There's a bunch of videos on YouTube. I'm sure you can find out if you want, and I would encourage that you would, because someone like that would deserve some recognition for that. Anyways, so here is something that's called a JK flip-flop. You can construct this out of various combinations of OR gates or NOR gates and AND gates and NAND gates. I tried to do that on the multisim, but multisim just would not cooperate. The clash with the reality was just too big for multisim, and here, you know, it is a complicated procedure to calculate all this, and I commend multisim for doing what they did. However, sometimes things do clash. All right. So, anyways, so here is an example of JK flip-flop, and we're going to analyze that. Now, I also would encourage you to find out how you can actually construct this out of NOR gates and AND gates and OR gates and NOR gate, NAND gates and AND gates and OR gates or NOR gates, NOR gates. Go ahead. Maybe even if you want, you can assemble those on the breadboard and confirm the functionality of those devices. However, they do come in packages. Here's an example of a package, a dual inline package, JK flip-flop, and the MS stands for master slave, because these two can be configured in as they can be configured as master and slave, which basically one feeds the other for the purpose of getting a cleaner and more stable operation. Here's another thing for you to find out what master-slave JK flip-flop combination is. All right, so now these are the two for S7476. That would be the TTL family of chips, of integrated circuits. And these, what does it say here? It says with preset and clear. So right away, what is the difference between the generic one that I found on Multisim? I'm pretty sure I could find out the particular one, but I just assembled that in two different ways. Actually, I'll give you one version of it, and here's an example of an integrated circuit that you can buy, which is configured slightly different. There are different variations of these devices available for whatever purpose you need or you would need. All right, so let's say the biggest difference in here is the way the clock is recognized. See over here, you can see that the clock is what if we have we see a little bit of a triangle, so that actually tells us that this is an edge triggered input. And what kind of an edge? Well, there is no bubble here, so this would be a positive edge triggered input, which means that when the input goes from low to high, then the condition is being recognized as a trigger. If it stays high, then well, good luck. It's nothing is going to happen. It's just during the time that this input clock goes from low to high, then something is going to happen here in this device. Now, in this 7476, the difference in the clock is that you can actually see the bubble here and the little triangular type of a shape. So this tells us this is the edge triggered, and this is a negative edge triggered. So this input would be triggered or would react to a signal that when it's fed into it, when the signal transitions from high to low. Okay, This one goes from low to high, from high to low. Now, the other thing, there's just a little bit of difference in naming things, but they mean the same thing. What is happening here? We have a set and preset inputs in labeled as the hard inputs or asynchronous inputs. And over here we have the clear and the preset terminals. So preset would be just the same thing as the set, and the clear would be same as the reset. Okay. Now also there is a difference in the triggering of these inputs. Okay, so this clear here is reacting, it's being active low, so normally it would be tied high, and when the signal goes low and stays low, this device would stay cleared. All right, so that would be the Q would be 1, and not Q would be 0. Sorry, not Q would be, okay, clear. Q would be 0, not Q would be 1. All right. Then if that one, the preset stays high, then no matter what happens to any of the inputs, then it will be preset to Q1, and of course not Q0. So over here, these are active, these inputs are active high, so I just put them normally to sit at 0. So if those, in this case, if those both of those inputs are sitting at 0, then the device will continue with a normal operation according to the synchronous inputs. Synchronous inputs depend on other things. The synchronous input depends on what the other conditions are, and depend of the other inputs. Well, the synchronous inputs depend on what the condition of other synchronous inputs are, plus what the condition would be of the asynchronous inputs, because these asynchronous inputs, in this case, they override everything. And as I said, well, the difference here is this will be active high, so they would be tied, they will be sitting low, and if these two are sitting low, then the whole circuit operates normally according to the synchronous inputs. And in this case here, they have to be, these two asynchronous inputs, they have to be tied high for the normal operation of this circuit. Let's look at the truth table of or the function table of this whole system here. Notice that right here we have this pulse generator that we just made in previous video, and we're going to use that to supply the clock input into this JK flip-flop, and we'll talk about why it actually is called a flip-flop device. All right, well, this truth table refers to this circuit that we just made here. Okay, now let's look at the inputs. Clock, and you can see the arrow going up, so that means the only condition that is basically listed here is when the clock goes high. So on the positive transition of the clock, something is going to happen. And let's see, JK, we have the basically binary combination or binary possibilities of all combination that we could have with JK. We could have both of them at 0, we could have 1, or we could have the other, or we could have both of them sitting at 1, which is basically listing all the possible combinations of 2 binary bits. All right, now we have the outputs here, Q and not Q, and of course the not Q complements Q by being the opposite of that. All right, now when let's see, when both of the inputs are tied low, then the clock transitions from low to high, because that's the recognized transition, because here is the clock, it's positively edged. All right, it's positive edge triggered. All right, so what do we have here? Both of them are sitting at 0, J and K, clock happens, so what do we have here? It says previous condition. So nothing is going to happen. Things are going to be latched as they were, right? Now let's say we bring the J to 1, and did I do this thing wrong? No, I did it right. Okay. For a second, I just doubted myself. All right. So we have J sitting at 0 and K sitting at 1. So, okay, so when the clock happens, this whole device is going to follow the J. So it's going to reset Q to 0. Okay. Now, if we have the other situation happening when J is 1 and K is 0, then of course it's going to follow the J. When the clock happens, it goes from low to high, then it's going to set Q to 1. Well, that makes sense. And here's the nice characteristic of a JK flip-flop, is when you have both of them sitting at 1, J and K sitting at 1, when the clock happens, the Q and the not Q, they toggle, which means whatever they were previously, they're going to flip the condition. Right? They're going to exchange. The 1 is going to become 0 and the 0 is going to become 1. They're going to flip. So that's why this device is called a flip-flop. When you set both of the J and K inputs at 1, and if you feed the clock, every time the clock transitions from 0 to 1, things are going to flip. Okay, the inputs, also the outputs, are going to exchange. It's just going to go this way or that way, this way or that way, like a teeter-totter. Okay. Now, these would be the synchronous inputs. Okay, the synchronous inputs depend on the condition of other things. Here's the asynchronous inputs. They do not depend on anything. They override everything. So I just listed that in this table right here. So you see that asynchronous inputs here, and it just basically says that clock, J, and K are going to be ignored. Okay, and I just put a little X's here with Q and not Q. So when the set, which is wrong mouse button over here, when this is set to 1 and nothing happens right now because the simulation is not on, then we're going to have the condition of a hard set. Okay, so which means Q is going to go to 1 no matter what else is happening with any of the other inputs. And then when the reset, instead the reset is high, then it's going to go in, the system is going to go into a hard reset, which means that the Q is going to be 0, and of course not Q is going to be 1. Now, set and reset at 0, then I said here we're going to continue with the normal operation, subject to the synchronous inputs conditions. So it's going to let the other inputs take over the operation. And here's an invalid condition, set and reset when they sit at 1. This would be an invalid condition. This is something that we don't want. And then device can't be set because the device cannot be set and reset concurrently, which means basically we cannot have reset and set at the same time, right? Because that would be kind of at least confusing. Right? Also, what I mentioned here is that set and reset terminals sometimes can be also called or labeled as pre and clear, or such force of preset and clear. And you might want to refer to the data sheets of whatever the device is to confirm the condition of those asynchronous inputs. All right, now, like for example here, right? Here's clear and preset, and here's set and reset. Different sources are going to label things a different way. Now, let's by all this talking here, let's just confirm the truth table. What I'm going to do is, now I'm going to explain this to you. Instead of drawing the resistor and going to the VCC and then tied to ground and having a switch, Multisim has something that's called the digital sources. Maybe I can quickly just jog one for you here. So if you go place, component, and let's just clear that here. We already have the sources set up here, and get digital sources, and you can have different type of digital sources, and this is the one interactive digital constant. So interactive, so that's the one you want, and you can just place this here, for example. And now let's just see what happens when we get probe sources, indicators. Let's go indicators. Let's get the red probes. Here's the probes, and probe red, because I like the red probe. Now I'm just going to place it here, close that, and I'm just going to make a straight connection of that source to the probe. And if I start the simulation, I can just see this one. If I switch, I just use here, it says key space. You can use space, or you can assign on the other key on the keyboard, but I'm just using the mouse and I'm clicking on it. So this would be high, that would be like about 5 volts, and this would be 0, low, would be 0 volts. Okay, so that's basically, instead of drawing all the resistors and the VCCs and all the connections, just to make things a little bit clearer, we can use those. So I'm just going to erase that for now, so we don't get any graphic pollution happening. All right, so let's turn this whole system on and see how it behaves. This is the JK flip-flop. All right. Yeah, I'm just going to make this a little bit clearer here. All right, so turn the simulation on. What do we see here? All right, so J and K, right here, J and K sitting at 0, and over here it says that previous condition is going to occur when the clock happens. Oh, let's confirm that. Here is the pulse generator that we have, the capacitor and 2 resistors, and I just made them all 10 kilo, which is fine. All right, let's just when we press that button, this clock is going to go high momentarily, and here is the probe that is going to indicate that it's going to blink for a short period of time. Okay, let's just see what happens. All right, the clock blinks, but because both J and K are sitting at 0, right, because they're tied to ground here, they're not connected to high. So no matter what we do with the clock, nothing is going to change on the output. Okay. All right. Well, let's see if we can get this condition right here when the J is high and K is low. So we should set that should set the Q to high upon the clock action. All right, which in this case it's a positive edge triggered. So when the pulse goes up, then the system should react. All right, so let's set the J to 1. Okay, so that's sitting at 1. So this J is sitting at high. It's sitting high. And then we're going to apply the clock. So then the situation what should happen is that you should set Q to 1, and of course not Q is going to be the opposite of that, because that's how flip-flops work and latches, that's how they work, Q and not Q. All right, let's apply clock. All right, watch what happens here. Boom. All right, there will be a flash, and here now then, no matter how many times you keep applying the clock, this here presets the condition that it should be until another condition happens. So let's just go the other way. Let's say K to 1 and J to 0. Here are the indicators, and apply the clock. All right, look at this. Let's do it again. J to 1 should set the Q. All right, and K to 1, that should set the not Q, and this should clear the Q. All right, okay, it works. Now here's a toggle condition. let's see what happens when we set both J and K to 1, and let's keep applying the clock. So now they're both sitting at 1, J and K, they're sitting at 1. So according to that truth table, we should see this thing toggle. All right, it toggles. Another pulse, it toggles. Another pulse, it toggles. So basically you can just keep applying the pulse, the clock pulse, and the outputs of the JK flip-flop are going to switch positions. So that's the idea of having the JK flip-flop. See, it toggles here. All right. Now we have toggled this thing for the Q to be 1. Let's see the asynchronous inputs. Let's say if set is set to 1, then it's going to get a hard set. No matter what happens, Q should go to 1. So actually, you know what? Let's just do the reset, because we right now we have the Q1. So if we do reset, then this whole system should go into the reset position. This is going to overwrite everything. So reset to 1. Okay, and then no matter what happens, no matter what you do with the clock, nothing is going to change that, because this overrides. Now, if we have the other one, then set to 1, set high, because in this case it's active high. In this case, it will be active low, so we will just have to do a little bit of switcheroo of the conditions. Now, then doesn't matter what we do, and we're going to have this whole JK flip-flop set to the set condition. All right, and then of course, if we want to resume now we should never have both of them at 1, because look. Over here, it just gave us both lights, both LEDs high, so we basically, it's an invalid condition, because we cannot have Q equal to not Q. It's just impossible. Q should be the opposite of not Q, and not Q should be opposite of Q. So this, both set and reset, should never be sitting at 1, both at the same time. All right. So yeah, let's just enjoy the operation of the JK flip-flop, which means we're going to set J and K both to high. There it is. And let's do some flip-flopping. All right, applying the clock. All right. Okay, so here is the idea of the JK flip-flop.